Hi guys, and welcome to Chapter 2. Chapter 2 is on matter, energy, and ecosystems, and so today we're just going to go over some introductions to matter and energy. We're going to dive into some basic concepts with physics, chemistry, and fundamental principles of matter, and then towards the end we're going to talk about some different principles of chemistry and biochemistry within ecosystems as well as different organisms. So let's dive in and start off with an introduction to matter and some fundamental principles of chemistry. Basically, matter is defined as all material in the universe which has mass and occupies space. And matter usually takes three forms. There is a fourth form called plasma that we're really not going to talk about. So for now, just think of the three fundamental principles of matter. Matter can take place as a solid, which is a state of matter characterized by particles arranged in such a way that their volume and their shape are relatively stable. So when you think of a solid, think a fixed shape as well as a fixed volume. Second, we have liquids. Liquids are a nearly incompressible fluid that conforms to the shape of its container but retains a relatively constant volume independent of pressure. So when you think of liquids, think of water. When you think of solid, think of ice. And when you think of a liquid, think that it has no fixed shape. If you put water in a cup, it'll take the shape of a cup. If you put the water in the shape of a different container, it will assume that container's shape. However, liquids, like solids, are not compressible. Their volume is relatively fixed, and so they really can't be compressed in terms of their volume. However, when we think of gases, gases are a substance or a matter in which they can expand freely and they can take up the shape of whatever containers they're in. So when you think of gases, think of water vapor, and gases are different from liquids as well as solids. When you compress a gas, it can shrink in terms of its volume. When you put a gas in a larger or a less pressurized tank, it will increase its volume. So gases can relatively change their volume as well as their shape. Liquids can change their shape but not really their volume, and solids cannot change their shape or their volume. So now that we've gone over the states of matter, it's going to be useful to go over some terms that dive into the specifics of matter and some of the fundamental principles of chemistry. Basically, an atom is the smallest chemical unit that retains the chemical properties of an element, and it's composed of three basic things: a proton, which is a subatomic particle with a positive charge, an electron, which is a subatomic particle with a negative charge, and a neutron, which is a subatomic particle with no charge. Out of the three of them, I would say the neutron is probably the least cool. It doesn't really do anything but take up space. Now, the protons and the neutrons are in the nucleus or the center of the atom. That's going to be the center that you see on the little diagram on your right-hand side, whereas the electrons spin on the outside of the atom and they're sort of in the periphery. Again, refer to the diagram at the bottom here on the right-hand side if you want to see sort of how an element is composed in the basic fundamental principles. Now, usually the electrons are displayed more recently in more of a cloud because their trajectories are a little more ambiguous than just these ellipses that you see around here, but this is basically how an atom is composed and structured. And in addition, we are going to talk about something called a molecule as well as an element. Now, a molecule is composed of atoms bonded together and different types of atoms bonded together. So this represents the smallest fundamental unit of a chemical compound, which can take part in a chemical atom. Now, a molecule can be two atoms from the same element, or they can be two atoms from different elements. And an element is a fundamental type of matter, and it's a chemical substance which can't be broken down into any simpler parts. An element is composed of a substance with the same type of atom. Basically, an element is composed of atoms with the same number of protons and the same number of electrons. And it can't be broken down into anything simpler without actually fundamentally breaking the atom apart into its component subatomic particles. And so molecules of an element are composed of the same type of atom. Molecules in something called a compound are composed of different types of atoms. So in an element, again, the molecules are composed of atoms with the same number of protons and electrons. In a compound, however, molecules are composed of atoms with varying numbers of protons and electrons. electrons. And so molecules can be composed of different types or different ratios of different types of elements, depending on whether that molecule is part of a compound or whether it is part of an element. And so when you think of elements, think of helium atoms or oxygen molecules on the left-hand side of this figure. And when you think of compounds, think of water, which has hydrogen atoms bonded with oxygen atoms. And so these compounds have different types of atoms composed together to form a different substance altogether. But if you notice, when I was talking about the difference between elements and compounds, I said that the atoms varied in terms of their protons and their electrons, but not in their neutrons. And that's because protons and electrons are what fundamentally govern the characteristics of an atom, not the number of neutrons. Remember that neutrons don't actually do anything, they just take up mass. And so that's where when we differentiate between atoms with the same number of protons and electrons, but varying numbers of neutrons, we call that an isotope. Now, this doesn't actually change the properties of the atom. What it does is it changes the mass of the atom, and it tends to increase the density, basically how much mass per unit volume an element has or the compound has. So if an element is composed of isotopes of an atom that have higher numbers of neutrons, that element tends to be more dense, but it fundamentally performs the same way when we look at how it reacts in chemical equations. And isotopes will be really important when we talk about radioactive isotopes, all the way in the nuclear energy section of non-renewable energy sources, I think in chapter 15, and that's going to be way down the line later on in the course. However, for now, what I want you to know is that isotopes vary in their density and the amount of mass that each atom has, but they fundamentally operate the same way when we look at their chemical properties. Now, over here on the left-hand side, you have three different stable isotopes of the element hydrogen. So hydrogen has one proton and it has one electron, but regular hydrogen just has no neutrons whatsoever. Deuterium has one proton, one neutron, and one electron, and then the isotope tritium has one proton, two neutrons, and one electron. So again, the number of protons and the number of electrons stay the same. What we're changing here as we're looking at different isotopes are the number of neutrons. And there are several fundamental properties of matter in chemistry that we're going to go over, particularly when we look at different chemical equations. And the first is something really important, and it's called the law of conservation of matter. And this says that matter cannot be created or destroyed. It can only be transformed from one type of substance into another type of substance. So atoms can't be created or destroyed. They can only be really rearranged. And that's what this fundamental law says. And this is really important when we look at different chemical equations, because whenever we look at a chemical equation, notice that the number of atoms don't change. The compounds in which the atoms are located change when we look at one side of a chemical equation to another, but the actual number of atoms do not. And that's really, really important when we're doing our chemical equations. So look at this typical combustion reaction. So when we have a combustion reaction, we have methane, CH4, so one carbon atom and four hydrogen atoms, plus two molecules of oxygen, so two molecules each having two oxygen atoms. And when we burn methane, so we react it with oxygen, it releases energy, and then we also get one molecule of CO2, so one carbon atom and two oxygen atoms, plus two molecules of water, each of those having one oxygen atom and two hydrogen atoms. So let's look at the numbers. On the left side of the equation, we have one carbon atom in our methane molecule, and we have four hydrogen atoms all attached to that carbon atom in that methane molecule. Now we also have four oxygen atoms, each bonded in the two different oxygen molecules. So to recap, four hydrogen atoms, one carbon atom, and four oxygen atoms. Now let's look at the right side of the equation. On the right side of the equation, we still have one carbon atom, and we still have four oxygen atoms. Two of those atoms are now rearranged to be bonded with the carbon atom to form a molecule of CO2, and the other two oxygen atoms are each bonded into a different water molecule. So you have one on the first water molecule and one on the second molecule, bringing us to a total of four. Finally, you also still have 4 hydrogen atoms, and each of these hydrogen atoms, 2 of which are going to be bonded to one water molecule, and 2 of them are going to be bonded to the second water molecule. So again, the number of atoms from each type of element that we look at in each side of the chemical equation is the same, and this is a principle of the law of conservation of matter. Now, the next thing we need to talk about is how atoms bond together in order to form these different molecules and these different elements and compounds. And for that, we need to talk about chemical bonds. Chemical bonds refer to the lasting attraction between atoms, be it ions or molecules, that enables the formation of chemical compounds. And this is fundamentally going to be with the transfer or the sharing of electrons, those negatively charged subatomic particles, on the periphery of different atoms. And there are 3 major types of bonds, 2 of which we're going to be tested on, 1 of which I added just for fun. The first major type of bond is something called a covalent bond, and this is going to be something on the left-hand side of your screen. In a covalent bond, electrons are shared between the orbits of 2 different atoms. So usually when we look at an atom, there is a certain number of electrons that atoms like to have in order to have what's called a stable electron shell. Now, valence electrons, or that electron shell, are kind of outside of the scope of this class. This is an introduction class. For that, go into some fundamentals or an introduction to chemistry. For now, what you need to know is that atoms like a certain number of electrons in order to have a stable, complete shell. And in reality, almost all atoms, as they occur naturally, don't actually have that complete shell. And so in order to achieve that complete shell, what they like to have, or that complete number of electrons, what they do is they either give away an electron or take an electron, or they share electrons. In a covalent bond, the electrons are shared. So, for example, in the case of 2 hydrogen atoms, the number of electrons that a hydrogen atom needs to have a complete electron shell, that number that it needs to be stable, is 2. However, naturally, hydrogen atoms only have 1 electron. So what they do is they form a molecule of H2, in which case 2 atoms of hydrogen covalently bond, meaning that they share each of their electrons, so that at any one given time, these electrons are shared between the 2 atoms. That means that each atom at some point has the complete number of electrons of 2 orbiting in their shell. Sometimes that's in one atom, sometimes that's in another atom, but by sharing the electrons in a covalent bond, each of these atoms gets the number of electrons that they need to be stable. Now, contrast that with what is called an ionic bond. And an ionic bond, basically what happens is that while some atoms have too little electrons to complete that outer shell, other atoms have one too many electrons to complete that outer shell. And so what happens is that one atom will actually get rid of its electron and give it to another atom that needs it. And so each atom then gets their own personal complete electron shell. So in the case of, for example, sodium atoms and chlorine atoms, sodium atoms on the left-hand side of your screen over here have 1 electron too many. It has 1 electron too many to have a complete outer shell. And so on the other hand, chlorine atoms need an electron. They have 1 electron too few to have that stable number of electrons that they like to be nice and happy. And so what's going to happen is that sodium atoms are actually going to give away 1 of their electrons to the chlorine atoms. And so what happens here is by sodium giving 1 of its electrons away to chlorine, both atoms, now called ions, are going to have the number of electrons that they like to be stable. Now notice that I stopped calling them atoms. Now we are calling them ions. And that is because these atoms no longer have the same number of electrons as they do protons. And what happens here is that these atoms no longer have a neutral charge. Remember that in a normal atom, the number of electrons are equal to the number of protons, meaning that the charges are equal. You have the same number of negative charges as you do positive charges. However, once an electron is given away or an extra electron is received, that no longer happens. And so then you get what are called charged atoms, or ions. In this case, sodium has given away 1 of its electrons. The number of electrons is now less than the number of protons in sodium, so sodium is now positively charged. However, Chlorine has just received an electron. Chlorine now has one too many electrons than it does protons, so chlorine now has a negative charge. And what happens here is, remember or keep in mind that opposite charges attract. So a negative charge and a positive charge attract one another. And so because these like charges attract one another, they are now bonded because of this mutual attraction. And that bond, the bond between ions, is what is known as an ionic bond. Now, there is a third kind of bond, James Bond, but he typically works at MI6, and while I encourage you to watch his movies because he's absolutely awesome, he's not actually relative to fundamental principles of chemistry or environmental science at all. I just think he looks cool and that he belongs on there. Now, this is chemical bonds, and these are some of the fundamental principles that we need to think about when we look at chemical reactions. It should also be noted that molecules are formed through the sharing of electrons. That's going to be those covalent bonds, while ions are formed via ionic bonds. And note that molecules and ions are not the same thing. They are fundamentally different in how they operate and how they perform in chemical reactions. Now, the next thing we need to talk about are acids and bases, and this fundamentally has to do with the molecule of water and the dynamics that water plays in how it binds to different molecules that are thrown into it and how it's attracted to different molecules that are thrown into it. Basically is conducive to the formation of acids and bases. Now, recall that water molecules are composed of one oxygen atom that is covalently bonded to two atoms of hydrogen. Basically, this is a covalent bond, so electrons are shared because oxygen needs 2 electrons to have that nice outer shell, and hydrogen each needs 1 extra electron for their outer shell. So by oxygen binding to 2 atoms of hydrogen, all electrons are shared and all 3 atoms are happy. However, in any aqueous solution, small numbers of water molecules split apart. Basically, oxygen can be kind of an electron hog, and so the force that oxygen holds onto those electrons can be so powerful that it actually can kick one of the hydrogens out of the covalent bond. Basically, what happens here is that the oxygen is now covalently bonded to just 1 hydrogen, but it has that extra electron, so it's technically actually an ion. And so this is called OH- because it is just an oxygen and a hydrogen atom, and it has an extra electron, so it's also an ion. And what happens is that in addition to that, the proton that has been spit out, that originally the nucleus of that hydrogen atom, is now just a positively charged hydrogen ion, meaning it is just a proton or proton and a neutron that has been spit out and is now positively charged. And because of this dynamic, this is conducive to the formation of acids and bases depending on the ratios of hydroxide, that OH-, or hydronium, that H+. So in pure water, this happens all the time. So water molecules will constantly be spitting out hydrogen atoms to form that hydroxide ion and that hydronium ion, and then in different areas, hydrogen ions and hydroxide ions are reforming to form water molecules. So this chemical equation, notice, has arrows going in both directions because this is happening over and over again. And in pure water, because the numbers of hydroxide ions and hydrogen ions are relatively equal to one another, this means that that pure water is approximately neutral in its acidity or its alkalinity. So basically, pure water is neutral. But however, pure water is actually really, really rare. It takes a lot of effort to get pure water, distill pure water from any sort of solution. So in reality, most solutions, or aqueous solutions, meaning solutions primarily composed of water, have all this stuff in it that it's kind of mixed in. And many of those aqueous solutions have different ratios of hydrogen ions and hydroxide ions. So when a solution is acidic, that means that it has higher concentrations of hydronium, or that H+ ion, meaning that it has way more H+, or those protons, in the water than it does that hydroxide ion, that OH-. However, basic solutions have way more OH- ions than they do H+. So depending on whether it has too much H+ or whether it has too much H- fundamentally determines whether a solution is acidic or whether it's basic. But it should be noted that both strong acids and strong bases are very reactive. Those H plus ions or OH minus ions really want to latch onto something. And so each one of them, depending on how many OH minus ions or how many H plus ions there are, means that these solutions can be very, very corrosive and very reactive. If the balance is way out of whack in either direction, meaning that if the number of H plus ions are way higher than the number of OH minus ions, that's going to be a very strong acid and it's going to be very corrosive. On the other hand, if a solution has way more hydroxide ions than H plus ions, that means that it's going to be a very strong base, and it's similarly going to be very, very corrosive. So in either direction, the farther you deviate away from a neutral solution, the more corrosive and the more reactive that solution is going to be. And in order to measure how acidic or how basic something is, we use something called the pH scale. And the pH scale basically is a range between 0 and 14 that measures how acidic or how basic a solution is. Now, the pH of water, something that is completely neutral, is 7. And the farther down you go, meaning that the lower that number is on the pH scale, the more acidic or the more H plus ions that solution has. However, if you go in the opposite direction, the farther up you go, above 7, that means that that solution is going to have more hydroxide ions relative to the number of hydrogen ions, meaning that that solution is going to be more basic. So at the low end of the spectrum, carb battery acid is going to have a pH of very close to 0. However, at the very high end of the spectrum, NaOH or sodium hydroxide is going to be a very, very basic solution. And again, remember that the farther away you deviate from pure water in either direction, the more reactive and the more corrosive that substance is going to be. You also should note that most biological systems need a roughly neutral pH, meaning that they need a pH around between the numbers 8 and 6. So you can't have a solution more than 8 and you can't have a solution less than 6 if you want things to live and thrive in it, meaning that strong bases and strong acids are both really, really harmful to biological organisms because they react with the tissues and the biological cells of those organisms. Now, I know this lecture is running a little bit long here, so for the last 3 slides, we're going to shift gears a little bit, and we're going to talk a little more about organic compounds. And basically, living things need both organic and inorganic compounds in order to survive and thrive. And when you think organic compounds, think molecules consisting of carbon atoms covalently bonded together with other carbon atoms, as well as additional types of atoms from other elements into these long chain or branching structures. Now, hydrocarbons are a type of organic molecule that is literally just carbon and hydrogen. And there are different species or different types of hydrocarbons. At first, at the most simple, you have something called methane, which is a carbon atom binded to 4 hydrogen atoms on either side. Then you have ethane, which are 2 carbon atoms bonded to hydrogen, propane, which is 3 carbon atoms bonded to hydrogen, butane, which is 4, and so forth. In addition to that, organic compounds become useful because carbon can be linked both in chains in the ways we've just talked about, as well as different ring-like structures. So in addition to these elaborate chains, they also form ring-like structures like the molecules below, where carbon is either bonded to other carbon atoms to form these rings, or carbon atoms are bonded to things like nitrogen and oxygen to form rings or other types of branching structures. Now, inorganic compounds, by contrast, lack these carbon-to-carbon bonds and might have carbon in them, but that carbon isn't bonded to other carbon atoms, and so these elaborate chains or branching structures no longer are able to be formed. And organic compounds compose a lot of the things that we really, really need in order to survive. And there are several different types that we're going to touch on right now. First are things like proteins. Proteins are organic compounds which produce tissues. They provide structural support. They're the things we need to build muscles and get strong. In addition, they also store energy and they transport different material. So proteins are really, really important types of organic compounds that we need to survive. In addition, nucleic acids, which are carbon to carbon and carbon to nitrogen organic compounds, form the hereditary information and are the basis of our genetic material. So DNA and RNA are very, very important carbon rings and carbon chain structures which contain all of our genetic information. Moving forward, carbohydrates are organic compounds which have a lot of those carbon to hydrogen bonds, which are energy sources that we can tap into in order to supply us energy to think, to move, and to operate. And in addition, other forms of energy sources like lipids are organic compounds which are fats and oils, and they also store a lot of energy and are really great for storing energy later on so that we need it. When you think of the difference between carbohydrates and lipids, think carbohydrates as instantaneous energy. We eat the food, we get the energy instantly. However, when you look at lipids are energy storage forms. So that's where we convert the energy from carbohydrates into a storage energy that we store as body fat in order to burn off at a later time when we get hungry and we don't have regular access to food. However, all of these organic structures are extremely important for the daily fundamental operation and existence of organic organisms. Now, speaking of energy, it would be really useful to briefly define energy before we go over the context of energy in biological systems. Energy is defined as the ability to do work, and work can be moving something, work can be thinking, operating, anything that is changing something from one thing to another. And there are different types of energy. For the sake of this class, we're going to focus on 3, and later on in the class, we're going to focus on a 4th one when we look at nuclear energy. However, for right now, think potential energy, kinetic energy, and chemical energy. And potential energy is the energy of position. It is energy that is currently being stored, but it's energy that we could capitalize on any given moment. So when you think of potential energy, think of a girl holding a ball over a cliff. The position of the ball above the cliff, where it could immediately be fallen and dropped, means that the ball has a high amount of potential energy. Kinetic energy is the energy of motion. In this scenario, if the girl drops the ball, the positional energy, that potential energy, now is converted rapidly into kinetic energy because the ball is shifting from its high position and rapidly speeding up in terms of its velocity. So it's falling faster and faster as it is now being allowed to be acted on by gravity. So potential energy is stored energy, kinetic energy is moving energy. And then chemical energy is a specific type of potential energy. Chemical energy is the energy held between bonds of different atoms, particularly covalent bonds. Recall again that atoms bond together chemically in a covalent bond when they are sharing their electrons. And that shared bond is actually really highly energetically valuable. And in the case, for example, of burning a hydrocarbon such as fossil fuel, what we are actually doing in reacting these different fossil fuels, these hydrocarbon chains that we just talked about, by reacting them with oxygen, we are shifting the bonds around and we are breaking the carbon-hydrogen bonds and we are releasing energy. And that energy is converted from that chemical energy, which is actually a type of potential energy. We are converting that into heat, into light, into electricity, into motion, whatever we need. And that conversion from chemical energy to kinetic energy is the basis for how we use energy for all of our society and all of our needs. Now, energy also moves through biological systems, and in a way we are actually all solar powered. Most of the energy that powers Earth's biological systems, in fact almost all energy that powers Earth's biological systems, mainly comes from the sun. And this happens through something called photosynthesis. Basically, organisms called autotrophs, meaning that organisms that use the energy to produce their own food, undergo a process called photosynthesis in which they react sunlight. They take light from the sun, react it with carbon dioxide in a way that produces sugars, which are carbohydrates, which they then use for energy. So basically, photosynthesis is the process of using carbon dioxide and sunlight to convert the sun's energy into a very high quality form of chemical energy, which the plants can then use later on. Now, the basic reaction for photosynthesis is that 6 molecules of carbon dioxide are reacted with 6 molecules of water as well as the sun's energy to produce sugar, which is a very complex carbohydrate. It has 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. That is a basic sugar molecule, as well as 6 molecules of oxygen. So again, photosynthesis takes CO2, water vapor, sunlight, and produces complex carbohydrates such as sugar as well as oxygen. And this is the fundamental way that we extract or convert the sun's energy into sources that are readily available for both plants and, by extension, everything that eats plants. And that is how, in a way, every organism is basically solar powered, because they use the sun's energy either directly in the form of plants or indirectly in the form of any other organism that either eats plants or organisms that eat organisms that eats plants. And so everything is basically relying on energy from the sun. Now, that is everything that we have for the first lecture for Chapter 2. I know this went a little over time. I apologize for that, but I look forward to seeing you guys again for the second lecture for Chapter 2, where we talk about systems and cycles. I'll see you then.